have to do as much as, it doesn't concern, size isn't as relevant as in this case. Because now we're not going down a column, we're going across the row. Now going across the row, nitrogen is less electronegative than oxygen, right? Just like in donation abilities, the less electronegative it is, the more easy it is to give up its electrons. So when you're doing a nucleophilic attack, you're giving up one of your lone pairs to form a new bond. So you're basically giving an electron to that electrophile. So because oxygen is more electronegative, it's a little bit more greedy. So nitrogen is less electronegative. It's not going to be as greedy. So nitrogen's going to win. So in this case, it's electronegativity. Right? And this is size or polarizability. Okay? Any questions? All right, number 8. Right, so now this is asking you to give the starting material any kind of electrophile, right? So this is giving a little more freedom because you can put a bromine or a chlorine, something like that, and the answer will still be right, as long as it makes sense. So we know that Ki looks like this, right? And iodine is pretty down the periodic table. It's pretty fluffy, pretty big. That means it's a very good nucleophile. Right? It's a good nucleophile, which means it's going to do a nucleophilic attack to get this, right? Now what happens is, when you do an SN2 attack, you get inversion. So you can think of it as an umbrella effect. For this one, as soon as you attack it, the hydrogens here is going to poof and go the other way. So all these hydrogens like that, as soon as you attack it, it's going to go like that, like an umbrella, you know, being blown out with the wind, really hard. Which means I can kind of draw it since it's going this way, and this is the nucleophile. The original way was kind of like that, so I would draw it like this. Okay, and then now I have to have some sort of leading group, right? And I can put a bromine or a chlorine, and not just use a bromine. It's easier. Okay, and this is the inversion. Now, if you figure out the R or S of this molecule, you would find out that it goes from R to S or S to R, one of those. All right, so that's what happens. And so let me show you guys this iodine here. Let's see. Right, the iodine has a lone pair. It's going to go to the backside attack directly behind this carbon bond to that bromine, right? That carbon-bromine bond is going to break like so, right? And if you draw a transition state, right? It would look like that, right? And so what happens is, as this bond forming, this bond's breaking, and so auto substitution is gonna start moving the other way. It's like the wind blowing at your umbrella, and your umbrella is going to get inverted. All right? So it's complete inversion. All right? Okay, so part B. If the starting electrophile, which is this, it says that if we assume that it's a chiral mixture, right, which means we only contain this and not the enantiomer, would the product be racemic or chiral? Well, if we have a nucleophilic attack and the solution and it ends up being a complete inversion, right, that would mean that if we start with the chiral starting material and this complete inversion, then the product should be also chiral. The solution should be chiral, not racemic, because we only have one enantiomer. So it's chiral. All right? Now for part C, if I add excess potassium iodide, right, which means that I react all of this and I get this product, right? But then I still have a bunch of potassium iodide left. Now the thing about potassium iodide, as it says in the hint, right? It has two properties. It's a good nucleophile, but it's also a good leaving group, which means that it can attack itself. Okay? So, with this, what can happen here is the iodine, since you have an excess of it, it will come in and attack it. Iodine is going to be the nucleophile, iodine is going to be the electrophile. It's going to leave, all right? And so now we have the inversion of steady center. Like that. And then you get I minus. What can happen again? Same thing, because now you're in excess. So it's going back and forth until it's just basically you get a mixture of the two, which means that your solution is no longer chiral and not as racemic. Because and this one is a thinking question. Are there any questions? Yes.
You said we start with chiral and our product is chiral. What if we start with achiral? Then what's the product will be?
Achiral. Because I mean, you have both enantiomers. You will get both enantiomers. But in this case, the biggest difference is that you start with a chiral molecule, right? Only one enantiomer of this, and then you put in excess potassium iodide, right? And so if you had only put just the right amount, you would only get this as your product, right? Because iodine will displace all the bromine, and then you get a perfect pure solution of that one enantiomer. But if you have more iodine, I minus around the solution, I minus is a pretty good nucleophile, but I minus is also a good leaving group. So what's going to happen is that it's going to racemerize, and it's going to basically attack itself, and just going back and forth until you get mixtures of both. Yes.
So the K doesn't matter at all.
No, the K in this case is just a spectator ion.
Okay.
Right? It doesn't do with the reaction. If I had put I minus, it would have been the same thing. Right?
Are there any other elements that can do that, like I? Have that?
Bromine can do it also, but it's not as great. Because this is what happens in some reactions. When you have iodine as a leaving group, you also have iodine as a good nucleophile. So you end up losing that higher chirality, or that pure solution of enantiomers. This example. So, so, so you have to look at properties of a lot of different molecules and atoms and see their relationship to